In this video, I'll show how we use Theorem 1.10 to answer the question of if two graphs have the same degree sequence, then how are they related? And so the theorem says they're related exactly by a possibly empty sequence of two switches. That is, they might have been they might have been the same graph to begin with. So how does this use Theorem 1.10? We'll see that come up. But the idea is to prove this by induction. Proof, sketch. So, right, we can look at all the graphs with n less than or equal to 4. And in fact, the book does this. It lists all the graphs, and I take it upon you. You can look at the degree sequences there, and you can see that any two graphs that have the same degree sequence, that can be changed into one another with a sequence of two switches. For n greater less than or equal to 4, the theorem holds. Again, we can just check that the theorem holds. So we can assume, this provides a base for induction. So assume n greater than or equal to 5, and now our induction hypothesis that any two graphs of order, let's say n minus 1, so one less than the case that we're considering. So any two graphs of order n minus 1 that have the same degree sequence are related by two switches. Right, we have our base, n less than or equal to 4. Here's our induction hypothesis. And so we need to show now that if we have two graphs of order n, right, one more than our induction hypothesis, that they can be transformed into each other by a sequence of two switches. So let G and H be two graphs of order n with degree sequence D1 greater than or equal to D2, greater than or equal to dk. And once more, we're going to use this set GS so that degree of VI is exactly DI, right? So we've labeled these in this non-decreasing or non-increasing way. That is, we're satisfying the conditions of Theorem 1.10 by just labeling our vertices in the right way. So what we're going to do, we're going to use Theorem 1.10 here. So let's say by Theorem 1.10, we can take our graph G, right? This is some graph in this set G sub S from Theorem 1.10. And so we can turn this into a graph G1 using two switches. And G1 has the property that neighborhood of V1 is this set, right? V2 up through V delta plus 1. With this case. And we can do the same thing with H. So we can also do a series of two switches to make sure that its vertex 1, let's call this graph H1, that its vertex 1 also has this property, we're calling this W, also has the property that the neighborhood of V1 is equal to W. So remember, this doesn't mean that the two graphs are the same yet. So maybe G looks something like this, or both of our graphs have this sort of general idea going to them, right? They're adjacent to all these first few vertices, and then not adjacent to the rest. Maybe I'll draw one more, so that's not adjacent to that one. V1, V2, V3, up through V delta plus 1 is adjacent to all of these. Oh, sorry, V2, V3, V4. And not adjacent to the rest of them. So they both have this structure, but maybe in G1, maybe these two are adjacent and these two are adjacent. And in H1, maybe, I don't know, maybe they're not adjacent, but maybe we have V3 and V delta plus 1 is, and this one. So the edges up here can change around and stuff. This is why we know G1 and H1 are not necessarily the same graph yet. We would have had to have gotten very lucky in order for G1 and H1 to be the same graph. It's possible we have different things going on up here. But here's the kicker. We're using induction, and I know that if I can reduce the order of these graphs by 1, then there'll be 2 graphs that have the same degree sequence. If I can ensure, I need to ensure that they have the same degree sequence. I really need to make sure of that. So I want to remove vertices from each of them, make sure it has they both still have the same degree sequence. And once I know that, then my induction hypothesis kicks in, and I can assume that there's some sequence of 2 switches that makes those 2 look like each other. And then I just add this vertex back in, and we have 2 graphs, G and H, can be made by each other with 2 switches. So, right, so I kind of just talk through the remaining parts of the proof, but let me draw it out in a little bit more detail. So now, right, we need to ensure that they have the same degree sequence when we remove this vertex so that we can use the induction hypothesis. But that's the whole thing with Theorem 1.10, is it tells us which vertex we can remove from each one and not disturb the equality between the degree sequences. So that is, we're going to remove V1 from both of them. Sorry, G1, H1. We're going to remove V1 from both of them. And since they were both set up in this way, when we remove V1, we also remove 1 from the remaining degrees. So like, let's say my degree sequence is something like 5, 4, 4, 4, 3. I'm not guaranteeing this is graphical or not. I'm just trying to illustrate how this is going to work. I want to make sure it at least is even. 12, 15, 19, 24. Let's put another 2 on there, something like that. I don't know if this is graphical or not. But the idea is this V1, right? This is the degree of V1. And when we remove V1, we take that off the degree sequence, but then each of these degrees is reduced by 1. So now this turns into a 3, 3, 3, and I do that for however many vertices this was adjacent to. So 5, 1, 2, 3. I'll knock this down, and I'll knock this down. So we get 3, 3, 3, 2, 1, 2, 2, and I get another degree sequence. I might have to reorder it to now these 2's come before it, 2, 2, 1. So right, I might have to reorder it like that, but the key thing is that if they had the same degree sequence to begin with, then since I now have this vertex I can remove, I can do this process with both of them and get them to have the same degree sequence, even get these 2 graphs to have the same degree sequence. So by this argument I just showed you, this little example, by this G1 minus V1 and H1 minus V1 have the same degree sequence. And our order n minus 1. So by induction hypothesis, they can be turned into each other by a sequence of degree 2 switches, sorry. So G1 minus V1 can be transformed by 2 switches to H1 minus V1. And really these arrows go both ways. So what's going on here? So remember we started with the graph G. We can use 2 switches to turn this into the graph G1 such that the neighborhood of V1 is how we want it. We did this with H. We also, we did this with H and made H1. Then we removed a vertex from each of these to get G1 minus V1, H1 minus H1 minus V1. Minus V1. And now these are order n, and so there's some sequence of 2 switches that we can do here. And then we can add this vertex back in. We can go the other way here and take these 2 switches. So this is sort of the chain of how we would get from G to H and H back to G via 2 switches. And right, we're doing this by induction. So eventually we'll get down to small enough, right, that we've already, we can do that. Right, this is how induction works. And so, right, that proves it. So any 2 graphs, same degree sequence. There's some set of 2 switches that takes one to the other.